Reinforcement learning is one of the most fascinating and foundational approaches in artificial intelligence. It's the same method that taught AlphaGo to defeat world champions, enabled robots to learn how to walk, and now powers dynamic decision-making in everything from finance to video games. But what exactly is reinforcement learning, RL, and how does it work? At its core, reinforcement learning is inspired by how animals and humans learn from experience. It's not about being told what to do, like in supervised learning. It's about discovering what works through trial and error. Imagine training a dog. You give it a treat when it performs a trick correctly. Over time, it learns to repeat the behavior that brings rewards and avoid actions that bring punishment. Reinforcement learning applies the same principle, digitally. In technical terms, reinforcement learning involves an harmless agent and base environment, and a system of rewards and penalties. The champ agent is the learner or decision maker, like a robot or a digital model. The hot environment is everything the agent interacts with, like a maze, a chessboard, or a stock market simulation. The agent observes the environment, takes an action, and receives our feedback in the form of a reward or penalty. The goal is to maximize cumulative rewards over time. This loop, observe, act, get feedback, is called the reinforcement learning cycle. The agent starts out clueless and improves as it explores different actions and their outcomes. The learning happens through a policy, essentially a strategy, that tells the agent what to do in a given situation. The better the policy, the better the agent performs. Reinforcement learning can be broken down into two main approaches. One, model-free learning, where the agent learns solely through experience without building an internal model of the environment. Algorithms like Q-learning and deep Q networks, DQNs, fall into this category. 2. Model-based learning, where the agent builds a model of the environment and uses it to plan actions. This is more like mental simulation, where the agent tries to predict outcomes before acting. Perhaps the most well-known breakthrough in RL came in 2016, when DeepMind's AlphaGo defeated Lee Sedol, one of the world's top Go players. AlphaGo combined deep learning with reinforcement learning to master a game with more possible moves than atoms in the universe. It didn't just memorize moves, it learned strategy. This opened the door to a new era of deep reinforcement learning, where neural networks are used to represent policies or value functions. These networks can handle high-dimensional inputs, like images or audio, and learn sophisticated behaviors. A popular method is the actor-critic architecture. Here, one network, the actor, proposes actions, while another, the critic, evaluates them. Together, they learn more efficiently than either would alone. In games like Atari, RL agents learn to play by watching pixels and maximizing their scores. In robotics, agents learn to balance, grasp, and walk through physical simulations before being deployed in the real world. In finance, RL models optimize trading strategies by learning from market behavior. So what makes reinforcement learning so powerful? It thrives in uncertain, dynamic environments. Unlike traditional optimization methods that assume fixed rules, RL adapts. It doesn't just react, it learns a strategy over time. It's useful in domains where labeled data is scarce, but interaction data is plentiful. However, RL has its challenges. First, it's sample inefficient. Agents often need millions of interactions to learn effectively. This can be expensive in real-world scenarios, like robotics, where each action has a cost. Second, RL can be unstable. Small changes in rewards, architecture, or randomness can lead to drastically different results. Researchers combat this with techniques like reward shaping, curriculum learning, and normalization. Third, exploration versus exploitation is a fundamental dilemma. The agent must explore new actions to discover better strategies, but it must also exploit what it already knows to earn rewards. Striking the right balance is key to success. Safety is another major concern. In critical applications like healthcare or autonomous driving, uncontrolled exploration can be dangerous. That's why safe reinforcement learning is a growing field, focusing on risk-aware policies and constraint-based models. Another exciting development is multi-agent reinforcement learning, where multiple agents learn in the same environment. This is especially useful for simulations of traffic systems, economic markets, or collaborative robotics. Agents must not only learn from the environment, but also adapt to the behavior of others. There's also hierarchical reinforcement learning, where agents learn high-level strategies that control lower-level actions. Think of it like planning a road trip, the big picture, while still navigating turns and signals, the details. This approach can speed up learning and improve generalization. In natural language processing, RL is now being used to align large language models with human preferences. Techniques like reinforcement learning from human feedback, RLHF, help transform models like ChatGPT from generic text generators into conversational assistants. Beyond the lab, RL is making its way into real-world systems. In recommendation engines, it personalizes suggestions over time. In energy grids, it optimizes load balancing and power storage. In autonomous drones, it navigates complex environments. In digital marketing, it adjusts strategies in real time based on feedback. So where is reinforcement learning headed? We're moving toward general-purpose agents. Systems that can learn multiple tasks, transfer skills across domains, and reason over long-time horizons. Integrating RL with memory, planning, and symbolic reasoning is a hot research frontier. We're also seeing increased interest in offline reinforcement learning, where agents learn from pre-collected data instead of real-time interaction. This makes RL safer and more applicable in sensitive fields. And finally, there's the human factor. More and more, reinforcement learning is being used not just to train machines, but to co-train with humans. Systems that augment decision-making, suggest actions, and adapt to user goals could redefine how we interact with technology. In a sense, reinforcement learning brings machines closer to human-like learning, not just copying patterns, but learning from mistakes, adapting to change, and striving toward goals. It's not just a tool, it's a philosophy of intelligence. And while the math behind it can be complex, the core idea is beautifully simple. Try, fail, learn, improve, repeat. That's reinforcement learning. To deepen our understanding of reinforcement learning, it's worth exploring some of the techniques researchers use to make RL more efficient and practical in the real world. One such approach is just reward shaping. In many real-world problems, simply giving the agent a final reward, e.g., win or lose, isn't enough. Reward shaping involves giving smaller intermediate rewards to help guide the learning process. For example, in a maze, the agent might receive small rewards for getting closer to the goal. Another valuable method is imitation learning. Instead of starting from scratch, agents can first learn by mimicking expert behavior, like watching a human play a game. This gives the agent a useful starting point before it begins reinforcement learning. A variation of this is inverse reinforcement learning, where the agent infers the reward function that the expert must be using, then optimizes for it. Curriculum learning is also gaining popularity. Just like human students, AI agents learn better when training progresses from easier tasks to harder ones. By starting simple and gradually increasing difficulty, agents learn faster and more reliably. In the deployment phase, policy distillation allows researchers to transfer knowledge from a large, complex agent into a smaller, faster model that's easier to run in production. This is particularly useful in mobile robotics or edge AI applications. There's also growing work on meta-reinforcement learning, or learning to learn. These agents aren't just learning tasks, they're learning how to learn new tasks more quickly, enabling rapid adaptation in changing environments. And let's not forget about ethical considerations. As RL becomes more autonomous and embedded in decision-making, ensuring fairness, transparency, and alignment with human values becomes critical. Researchers are exploring how to integrate ethical constraints directly into reward functions or through human-in-the-loop feedback. Finally, advances in simulation platforms like OpenAI Gym, DeepMind Lab, and Unity ML agents have democratized RL research. These environments allow for scalable experimentation, visualization, and benchmarking, accelerating innovation across the board. So while reinforcement learning began with games and toys, it's now pushing the boundaries of what machines can achieve into the real world. From self-driving cars and recommendation engines to language models and robotics, reinforcement learning is no longer niche. It's the engine behind intelligent behavior. And as it continues to evolve, it won't just teach machines how to learn. It'll help us understand how learning itself works.